Natural disasters such as earthquakes, landslides, and forest fires occur almost on a daily basis. It's important to study these systems to be able to help predict and prepare us for them. However, these systems are very complex. Oftentimes, to understand a complex phenomena, a simple system with the same phenomena can be examined. For example, to understand some natural disasters, a simple pile of beads can be considered. For my senior independent study, this is what I've been working on, experimenting with a bead pile system. In the experiment, the addition of beads increases the pile size, and eventually even the addition of a single bead can cause an avalanche to occur. So by studying the sizes of avalanches and the times when the avalanches occur, we can better understand the dynamics of bigger systems, allowing us to better predict the occurrence of some natural disasters. This is great, but sadly it takes a week to record data for one experiment to run. A virtual pile allows us to run the experiment much faster and gives us more control over the experiment. In a virtual simulation, we're the overlords of the virtual world. This is the core of my project, a creation of a virtual bead pile that exhibits the same physics as the actual bead pile. To do this, we use graphical processing units, or GPUs, instead of traditional central processing units, or CPUs, for computations. Think of CPU processing as one student doing 20 homework questions alone, and GPU processing as 20 students dividing the 20 questions amongst each other. The 20 students, independent minds working together, will be able to solve the homework set much quicker than the single student. The simulations I made do in fact run much faster than the actual experiment. The first simulation uses NVIDIA Flex, a physics engine that incorporates complex computer science algorithms and runs 34 times faster than the actual experiment. However, Flex is proprietary, so we can't really modify the physics code. In other words, we can't really choose the physics that's going inside the virtual world when using Flex. We want to be able to choose the physics we put into our system so that we can determine the underlying fundamental equations that govern these large-scale natural disasters. Hence, we created our own physics engine that used only conservation of energy and momentum initially, and then provided some energy loss after collisions occurred. Initially, the simulation didn't quite match up with the experiment, and we think we know why. It's because there's no friction in the model. The beads are too slippery, and so we can't really get the large-sized avalanches we expect. We've derived equations for a physics engine that incorporates friction, and have begun working on that. So, 30 years ago, the bead pile experiment began as an independent study, and now it's helped shape mine. I, in return, have created the groundwork for another student to carry on the work of understanding avalanches with the simulation. In the past 4 centuries, physicists have been trying to better understand the universe. Here at the College of Wooster, we hope to do the same by contributing a small bit with a simple experiment of a bead pile.